Chemical kinetics deals with how fast a reaction happens. In other words, you can think about how fast the reactants are being converted to products. So I have here several representations for the same thing. Your reactant being converted to product. So I have my reactant here, A going to B, which is my product. And you start with only A, that's your reactant, and then over time, your reactants start being converted to product until you have everything as a product. Ideally, this is what you want. Now, another representation for the same thing is this graph here. Graph of concentration versus time, or how the concentration is changing over time. And I'm showing you here concentration for both your reactant and your product. And this is a simplification because you have only one reactant and you're getting only one product. I'm adding some numbers in your graph because I want to explain something with those numbers. This is just a generic representation. I'm using numbers so you can actually come back later and see what those numbers represent. So I have two different colors, one for my reactant A, and that curve right here, it's representing the concentration of A, or what's happening to that concentration over time. So you can see that the concentration for your reactant is going down over time, and that it's happening because your product is being formed and you're getting the product from your reactant. So as the concentration of your reactant goes down, the concentration of your product is going up over time. So we can actually determine like how fast a reaction is happening if you check the change in the concentration of a reactant or a product over time. So usually we write down rate that's a delta, which means change, or a final minus an initial. And I'm going to do this for the reactant because that's the one that I want to explain, and I will give you like a brief description of what's happening with the product after. Change in the concentration, brackets, is what we use to represent molar concentration. Over change in time. Or you can check the concentration of your reactant at two different points over time, and you can calculate the rate looking at the difference in the concentration and the time. And when you're calculating a difference, that's always final minus initial, and the same thing applies with your time. Final time minus an initial time, and all of those numbers are relative. You can select at what time you want to determine the concentration. Okay? You can choose that one as your initial and then another time for your final. So I'm going to use my numbers, the ones that I have in my graph, to show you what's happening with the concentration of A using actual numbers. So I have my 4 here, and that right there is your concentration 4, and that's going to be happening at approximately 3, and let's put that as in seconds. So at after 3 seconds, you have that concentration of your reactant, 4 molar concentration. We're using molarity, you have brackets. Then I have here for my reactant, when the concentration is 2, I'm at this point right here, and that will be at 12 seconds. So I'm going to label this TF because I'm selecting that one as my final time, and this one here as my initial time. Your concentration, this is your initial, the one that it's happening at 3 seconds, so that will be and your concentration is down. After 12 seconds, your concentration now is 2. So to calculate the rate, you can use those numbers. And that's for A. Your final concentration is 2. Your initial concentration is 4. Your final time is 12. And your initial time, or the one that we're using, is 3. You can see that this here is going to give you a negative number. That's 2 minus 4. That's a negative 2. And then you have 12 minus 3, which is going to give you 9. So you can simplify that. I'm rounding to two significant figures. So negative 0.22. So the negative sign, you're going to get a negative sign always for the rate of a reactant, because the concentration of your reactant is decreasing over time. That negative sign is telling you how much the concentration is changing in that specific interval of time. So when you go from 3 seconds to 12 seconds in this example, the concentration of your reactant A is decreasing by 0.22. So molar over second, every second that's passing by in this reaction, your concentration is going down by that amount. The negative sign is telling you that it's changing by or decreasing by that number. So concentration rate, you will have units of molarity over seconds. So it's telling you that the concentration, molar concentration, is changing by that much every second that your reaction is happening. So I wanted to go over this because of the negative sign. The negative sign is not that you have a negative rate, it's just telling you that the concentration is decreasing over time. And that's going to happen only with the reactant, because your concentration for the product, that one, it's increasing over time. So that one, you will get a rate that it's a positive number. So usually when we have a rate for any reactant, we use a negative sign in front of, just in case if you see something like that. So that negative sign is there to cancel. The negative sign that you're getting for the change in the concentration. Nothing else. Now, chemical kinetics is not only telling you how fast a reaction can happen, but also the things that you can change or improve in a chemical reaction to make that reaction go even faster. So we have here the collision theory of kinetics, and this is telling you how, like, when your particles are colliding with each other, the reaction is going to actually happen, and you're going from your reactant to your product. But it's not just any possible collision. We need effective collisions, and by effective collisions, what that means is that you have collisions between your particles with enough energy and a proper orientation. Enough energy to break chemical bonds, right? You're going from reactant to product, so you're breaking chemical bonds on your reactant side and you're forming new chemical bonds on your product side. So your collisions, they need to have enough energy to break those chemical bonds on your reactant side. And your molecules, they have to collide with a proper orientation. You can have a billion collisions between your particles, but only some of them are going to be actually effective. Yeah? So I do this simple representation to go over this. I have CO plus O2 going to CO2 plus single atom of oxygen. So I'm going to use two different colors, one for the carbon, one for the oxygen. So this is CO dot for C dot for O. This is 2 oxygen, so I'm going to put 2 for the same color there. Now CO2, I have carbon. I'm going to put 1 oxygen here, and then for oxygen. So it's the same thing, but using just dots representing your atoms with different colors. So we have possible collisions, and I'm going to do just one example of something that it's not going to work out, and then one example of something that has a proper orientation, and it will give you an effective collision if you have enough energy. So if your CO, like this, that orientation collides with your molecule of oxygen in that orientation going this way, assuming that you have like enough energy, that's going to look like this. One, two, three. So your carbon, you want CO2, right? And you have 3 oxygens there. So if that oxygen leaves, that's going to give you this right here. Plus the oxygen that it's leaving. So that's an example of a collision that has not the proper orientation. You don't have the proper orientation because your carbon dioxide, I'm writing that one down as blue, pink, blue. Okay? And what you're getting here is not the same thing. So a proper collision will probably look, with my representation, you need to have something like this. Your carbon dioxide needs to be in the opposite direction. The carbon looking towards your oxygen molecule. Now that's going to give you this. That. The then I have the pink, then I have two blues. Now, if the oxygen atom leaves, you're going to get the blue, the pink, the blue, plus the oxygen atom that is leaving. So if your collision happens with this specific orientation here, you actually are going to be forming the product. Right? So that's what a proper orientation means, or what we can use to represent a proper orientation. So you have that the more effective collisions you can get, the faster the reaction will happen. That's what the collision theory of kinetics is actually telling you. So based on that theory, we can go over things that are actually going to speed up a reaction, or that can help. So I have 4 different things. The first one is the nature of the actual reactant. And for that one, we can think about different things. The identity of the substance, because you have things that are more reactive than others. And I'm giving you one example. Your elements, calcium and sodium, they have a very similar reaction with water, but the rate of the reaction is very different among them. So for the place where sodium and calcium are in the periodic table, we know that sodium is more reactive than calcium, which means that you're going to get a faster reaction for sodium. Even though you have a very similar reaction, you're getting a hydroxide or a base for the metal and hydrogen gas forming. Those are the products for your 2 reactions, but the speed of the reaction is very different. So that's one thing. Another thing that you can think when you're looking at the identity of the substance or the nature of your reactant is how big or how heavy the substances are. Right? Like smaller molecules will react faster, and that is because smaller molecules will move faster, which means that you can have more collisions between them, and the speed of the reaction will be actually faster. Something similar is happening when you're looking at the physical states, right? If you have gases, liquids, and solid, your gases, your molecules are moving around all the time. They don't have any interactions between them. They're not attracting each other, which means that they're going to be moving freely. And since they're moving freely, they can have a higher number of collisions, right? And also because they're moving faster than the molecules in a liquid. And then in your solids, your molecules can vibrate. They're not moving around, so you should expect a slower reaction for solids. And then concentration of the reactant is my second factor. Okay? And this is totally related to your theory, the one that we just went over, the collision theory, because if you increase the concentration, it means that you have more particles of your reactants in the actual container. The more particles you have, the easier it will be for them to find each other, to have collisions to give you the product. Okay? So usually when you have a higher concentration, you're going to get more collisions and you will have a faster reaction. So there's not too much to add here, or nothing at all. And then my number 3, number 1 is the nature of the reactants, then concentration, and my number 3, or the third factor, is the temperature, which is also 100% related to your collision theory of kinetics. In general, increasing the temperature will make a reaction go faster. When you're increasing the temperature of something, what it's actually happening is that that substance is gaining kinetic energy, which is that energy associated with movement. So you can think of increasing a temperature and your molecules start moving faster because they have more kinetic energy. Since they're moving faster, you're going to have more collisions, which can result in a higher number of proper collisions and in a faster rate. We have the Arrhenius equation here, which is relating like the rate constant, which is the first time that we see that one, with the temperature, and we're going to keep using the rate constant for the remaining of the topic. So in this equation, we have several things. We have our rate constant, which is just a number that tells you or gives you an idea of how fast the reaction is happening. We have that letter A, which is a frequency factor. That frequency factor, it's a number that it's telling you like how many collisions you have or how frequent your particles are going to collide over time. It's a number in units of seconds to the -1, like 20 seconds to the -1 means that you have like about 20, like the frequency is about 20 collisions per second or something like that. Then this is the Euler's number. It's a mathematical operation. And that number, it's increased to the power of something. And that something we have there. EA is the activation energy. And we have the definitions here for everything. Activation energy is just the minimum amount of energy that it's required for your products to actually go towards the reactants. R is the gas constant that you know, but we have a different number because we're using different units. We have units of energy here, so we need a number with units of energy. And then T is the temperature. Temperature in kelvins because we have kelvins for the units of that constant. I have here the definitions for activation energy, your frequency factor, and your gas constant. You see, you probably know the number as 0.082, but that one has different units here. So this is the one that we're using, but it's the same constant, different magnitude because we're using different units. And temperature in kelvins. So the equation here, or the calculation, is not too important. I'm going to show you like an example, and then you're going to do your own calculation and you can compare your numbers. But what this is telling you is that as you increase the temperature, this number here is going to be bigger. So remember, the calculation is not the important part. The important part is the relationship between your rate constant and the temperature, or the rate of a reaction and the temperature. but you do need to know like what A is and activation energy and all of that. So I'm giving you just numbers for you to calculate the rate constant. And the calculation is pretty easy. You just need to plug in the numbers in the equation. The part that it's like a little bit complicated and that might result in you getting a different answer, it's how you plug in that in your calculator. Okay? So I have here my frequency factor at 2000, activation energy, the temperature is 298, and you have your value for the gas constant. Activation energy, and that's divided by the temperature is 298 kelvins. So depending on your calculator, you will have to do like this in one step and then find the inverse function of your natural log, which is that E, and then that number times the frequency factor. Another thing that you might do is put those two numbers in parentheses. Okay? If you don't put parentheses, your calculator might be doing 222 divided by 8.314, and whatever number you're getting for that division, multiply by 298, which is going to give you the wrong answer. Another possible option is for you to forget about that negative number. That's also going to give you the wrong answer. If you solve this, that's going to give you something close to this number. Units of second to the minus 1. You can check that all of the units are canceling out. The only unit that is not canceling out is the unit that you have for the frequency factor. So make sure that you try to do and you plug in the numbers in the calculator to make sure that you're actually getting that one right there. You can calculate the same thing. Let's put 1 here. Use the same numbers but a different temperature. You can choose whatever temperature you want. I'm going to give you 398 kelvins. And whenever you have time, do your calculation and you should get something close, depending on your rounding. If you're calculating this in one step and different steps, you might get something a little bit different. But you should be able to see that when your temperature is 298, a lower temperature than 398, your rate constant is a smaller number. And if you have time, you can do the same calculation with a lower temperature, lower than 298, higher than 398. And the same trend should happen, like higher temperature, higher rate constant, or lower temperature, lower rate constant. And the last factor that we're going over that is going to affect the rate or the speed of a reaction, it's the addition of a catalyst. Okay? So a catalyst, it's something that is going to give you like another way for you to go from reactants to products. Okay? So if you don't have a catalyst, you're going from reactants to product and maybe different steps. Then if you have a catalyst, you will go from reactants to products using a different route. But what actually is the catalyst doing is finding a way to decrease your activation energy. And remember, like, your activation energy is that amount of energy that you need for your reactants to actually go to products. If you don't have that minimum amount of energy, your reactants will not move towards the products because you don't have enough energy to like jump towards or through that barrier. So I have a graph representing like your chemical reaction, A towards B. I have A here. This is energy, reaction, progress, no concentration, nothing like that. It's just a representation. So for your reactant to go all the way to products, and I'm looking at the black line here, you need that minimum, at least that amount of energy. You see, this is energy here. You need at least that amount of energy for the reactant to actually go towards the product side. So this is representing a reaction without a catalyst. If you add a catalyst, your catalyst is going to find a different way for your reactant to go towards your product, and that new pathway is going to have a lower activation energy. You see, for your reactant to go towards your product without a catalyst, it's going to take a longer time for it to reach that minimum amount of energy. When you add your catalyst now, the amount of energy that you need to actually go from reactants to products, it's lower. So the red one, it's representing what's happening when you add a catalyst. There are many different catalysts and they work in different ways. What they have in common is that all of them are decreasing that activation energy. Some catalysts will break the chemical bonds on your reactants faster, or they will bind to your reactant and will give you like a better orientation for your reactant molecules. They do like different things. But all of them, they have in common that trend, that they will decrease the activation energy. So this is something for you to find out, okay? There are different catalysts, homogeneous and heterogeneous. You should find out what it's the difference and similarities between them, and just make a small note about them. You don't have to go finding specific examples or anything. Just the definitions, what do they have in common, which I already told you, and what is different between homogeneous and heterogeneous catalysis. Now, it's important for you to know that the only effects a catalyst is having on your reaction is decreasing that activation energy. The catalyst is not participating in the reaction, it's not forming a different product. Your reactant is being converted to products, same reactant, same products, with or without the catalyst. The only thing that the catalyst is changing is that activation energy. Now, the other factors, the nature of your reactant, the temperature, and the concentration of your reactants, all of those are going to increase the rate of your reaction. Okay? But none of them are affecting the activation energy. Okay? All of them are related to the number of collisions that you have. Okay? Increasing temperature, increasing kinetic energy, increasing the number of collisions, increasing concentration, increases the number of collisions and increases the rate. Okay? None of them are actually changing the activation energy. The only thing that will change your activation energy is a catalyst.